All right, good afternoon, everybody. So that last question was actually a good segue into this talk. So I'll try to convince you that we don't necessarily need a laser for on-chip photonics. We can actually use an LED. All right, so let me try to motivate this research. We've actually talked about this quite a bit in this venue. So one of the challenges right now in computing is really reducing the energy costs for communication. So on chip, we're really constrained by the capacitance of wires. We can help ourselves out quite a bit if somehow we can replace one or more of those electrical interconnect layers with optical interconnects. And the reason is simple. Photons aren't charged, so we don't need to worry about charging up a capacitance. And in principle, we could operate with as low as attojoules per bit of energy. So to do this, though, we really would like to have a light source that's tightly integrated with the chip. And we want it to be tightly integrated, so it needs to be nanoscale, it needs to be fast, and it needs to be efficient. So the obvious approach would be to think about using a laser to do this. Now we can talk generally about the properties of lasers. One of the main properties of a laser is that to turn it on, you need to reach some sort of threshold current. Okay, so below the threshold current, you get light out, but it's not usable light. The modulation bandwidth, so how quickly we can turn on and turn off the laser, it turns out that you can get modulation bandwidths approaching 50 gigahertz or so, but you have to pump quite a bit of current into the laser to do this. So inherently, the laser is a pretty power-hungry device. Now you could also use, going the wrong way, you could also use a light-emitting diode. Now, a light-emitting diode has some nice properties. We don't need to worry about a cavity, so we can scale the light-emitting diode into the nanoscale relatively easily. We know from solid-state lighting that's all around us that LEDs can be made very efficient, but the problem is that they're rather slow. So the modulation speeds of LEDs is typically limited to a couple of hundred megahertz. So let's talk a little bit more about that. Why is it so slow? So light emission in an LED, of course, is from spontaneous emission. Now, spontaneous emission is from optical dipole transitions between electrons and holes, but we can think of it more simply as little oscillating dipole currents in our semiconductor material. Now, these dipole currents are very, very small with respect to the wavelength of emission, and we know from antenna theory that that does not make for a very good, efficient radiator. So in other words, we can effectively say that a semiconductor acts as a poor antenna for its own radiation. Now, if we take a good antenna, say a lambda over 2 size dipole antenna, and we attach it to our semiconductor material, we can actually boost up the spontaneous emission rate rather dramatically. You can show that you can enhance the spontaneous emission rate by a factor of the antenna length, which is on the order of lambda, the wavelength of the light, divided by the antenna gap spacing here, d. So the wavelength is, on the order of hundreds of nanometers, and so if you can scale down the antenna gap, if you can scale down your semiconductor and fit it into this feed gap in the nanoscale regime, you can get a large enhancement of your spontaneous emission rate. And by doing this, we can now think of, instead of a light-emitting diode, an antenna LED. And in fact, we can boost up the spontaneous emission rate so much that it is faster than the stimulated emission rate and faster than the laser. We can modulate these devices in excess of 100 gigahertz. Now, this idea of using antennas for spontaneous emission enhancement has been around for some time. There are a lot of reports in the literature, and I just kind of give you a few of the reports to show you an idea of what people are typically doing to enhance spontaneous emission. And the simplest way to do this is just to simply pattern some sort of antenna on a substrate and sprinkle a light emitter around the antenna. It could be a quantum dot or a diamolecule. And those molecules or light emitters that kind of fall right within the antenna mode will have enhanced spontaneous emission. And many groups have reported similar structures. Semiconductors, on the other hand, there's been less attention on using semiconductors. One of the early approaches was to take kind of a traditional epitaxial stack of materials and then pattern a dipole antenna near the active region to get enhanced spontaneous emission. Now, there's been a lot of diverse approaches, a lot of different materials, a lot of different antennas, but most of these reports have one thing in common, and that's that they use optical pumping to excite their light-emitting materials. Now, we're thinking about using an antenna for a communication device, and so practically speaking, we really need electrical injection if we're going to make this work. So the past few years, we've been working on this device, which is an electrically injected 3.5 LED that's coupled to a slot antenna. Now, how does this work? It's made actually relatively easily. What we do is we dry etch these nanoscale PN junction 3.5 ridges, and then we cap the ridges with a metal, usually silver or gold. Now, if you design the geometry of this ridge correctly, this will naturally form a slot antenna. And if you design the geometry correctly, the resonance wavelength of that antenna will overlap with the emission wavelength of the active region, and the active region will have enhanced spontaneous emission. Now, there's a number of advantages to this approach, and probably the most important is that electrical injection in this device is straightforward. So what we can do is we can use the antenna metal itself as an N-type contact. So these particular materials are indium gallium arsenide active region cladded by N-type indium phosphide and P-type indium phosphide. And so we use the antenna to electrically contact the N-type material, inject electrons into the active region, and then use the P-type substrate to inject holes. And then we can get enhanced light emission from the active region. Other advantages are that the light goes in one direction, so it's unidirectional, which is useful for waveguide coupling, which I'll talk about in a moment. And then we've shown also with this device, we can, in principle, achieve greater than 100 gigahertz direct modulation rate. Okay, so we've built the devices in the lab, and we've successfully measured enhanced spontaneous emission from the devices. And the way that we measured this was on the same chip. We had basically two flavors of device. One was the antenna LED itself, where the 3.5 active region was tightly coupled to the antenna. And then another device, which I'll call the no antenna device, where the metal was offset from the active region, and so it did not couple to the antenna mode. And so we measured the electroluminescence intensity from both devices, and what we saw were two strong effects. One is a large increase in the light intensity from the antenna LED device. And we also noticed that as we changed the geometry of the antenna LED device, we could shift the emission wavelength of the active region. And this is just simply showing how we can tune the resonance wavelength of the antenna by changing the geometry. Now, this particular device was operated in a regime where the non-radiative rate was dominant, and so we can approximate the quantum efficiency as being equal to the non-radiative lifetime divided by the radiative lifetime. So any kind of decrease in the radiative lifetime from your antenna is going to result in an increase in the intensity of your light emission. And keeping that in mind, that allowed us to easily extract the enhanced spontaneous emission from the antenna. And for the device in blue here, we measured a 100-fold increase in the spontaneous emission rate. So you can play some tricks to try to boost that number up even further. One of the more recent results we have was using a quantum well active region. This provides a little bit of better matching between the polarization of the light emission from the active region with the polarization of the antenna mode. By doing this, we did indeed see an improved performance, so now a 200 times increase in the spontaneous emission rate. All right, so you might ask, what about the time-resolved light emission? So we measure that as well. Again, this was measured for the no antenna device and the antenna LED device, and we saw something interesting. Indeed, the emission, the decay rate was very fast, less than 20 picoseconds, but so was the device without the antenna. All right, so what is this telling us? It's telling us that, as I showed on the previous graphs, we increased the spontaneous emission rate, but we haven't quite increased it enough to compete with the non-radiative rate. And so how do we fix that challenge? Let me try to first convince you that we can actually make this device efficient. It's well known that 3.5 materials tend to have poor surfaces, and it's rather challenging to scale these devices into the nanoscale regime and make them efficient because of the poor surfaces and relatively high surface recombination velocities. what ends up happening is that you inject current, and instead of going into the desirable radiative recombination, you get this undesirable surface recombination. Fortunately, though, we do have the antenna here, which is boosting up the spontaneous emission rate with respect to the non-radiative rate. And so what we can do is we can easily quantify these, the radiative recombination current and the surface recombination current. And I do this for, I just assume an indium gallium arsenide active region with a surface recombination velocity of 10,000 centimeters per second. And I assume that the device is fully turned on. And I plot these two currents, the desirable radiative current and the non-desirable surface recombination current, as a function of the antenna enhancement factor. And so what you see is that if you have a big enough boost in the spontaneous emission rate from your antenna, your radiative current can actually exceed this non-radiative surface current, and you can have efficient operation of this device. You need about a 50 times or so enhancement of the spontaneous emission rate. And so I've already showed you that we can achieve this. So why haven't we seen the efficient device yet? So it turns out that even this relatively high surface recombination velocity is difficult to maintain when you make a device. So what we've found out is in the process of fabricating these devices, of course, the active region gets exposed to the various process conditions. And because of that, somehow the surface is getting damaged and the surface recombination velocity increases dramatically, greater than 100,000 centimeters per second. This is shown in this time-resolved photoluminescence measurement from a device before processing, after the ridge was dry etched, and then after device processing, but before the antenna was added. And we can see a decrease in the decay rate just simply because of the increase in the surface recombination velocity. Now, fortunately, we have a way of dealing with this problem, and it's rather simple. So let me guide you through that process. So we first dry etch this nanoscale PN junction ridge, and then we immediately cap it with a protective aluminum oxide that's deposited via atomic layer deposition. And then after that, we do all of the peripheral processing to make the device, deposit the contacts, and so forth. And we can strip off that protective sacrificial aluminum oxide layer to recover the as etched surface. And it turns out that this does work, but it not only works, it actually somehow cleans the surface in the process. So very interestingly, we, after stripping off this sacrificial aluminum oxide layer, we saw a decrease in the surface recombination velocity below 10,000 centimeters per second. So I would consider that an ultra clean surface for this particular material, which is indium gallium arsenide. So we think we can use this approach now to make that fast and efficient light emitter. Okay, so let me talk briefly about some nice work that a graduate student is doing in the project. Nicolas Andrade has been doing some design work to try to couple these light emitters onto waveguides. So everything up to this point I've showed you has more or less been free space coupling, which is fine for experiments, but really we want to place these devices on chip. And so we need to couple the light into ideally a single mode waveguide. Normally, you think of coupling LEDs into a waveguide, you normally think of that being a challenge, right? A traditional LED is really, really challenging to couple into a single mode, say, optical fiber. But it turns out, in our case, it's a lot easier because we've scaled down the LED so much that it only emits into a single spatial mode. And now, because of that, your life is much easier if you're trying to couple that light into a single mode waveguide. And he showed a design that can actually achieve this. So he's able to couple the light from the nano LED with efficiency approaching 90%. It's broadband. And furthermore, it's done in a manner such that the light propagation is unidirectional. Okay, so let me go ahead and summarize. So demonstrated a 200-fold enhancement of the spontaneous emission rate in electrically injected 3.5 antenna LED. I tried to emphasize that despite the high surface recombination velocity of these materials, high efficiency is possible because of the enhanced spontaneous emission. But that's dependent on making sure that you have a very good clean surface to begin with, and I showed you how to do that with sacrificial aluminum oxide layer. and then finally show you that it is indeed possible to couple the light efficiently onto an on-chip waveguide. And with that, I just would like to acknowledge the funding sources and technical support. Thank you.